Ecco, adesso forse ho fatto tutto. Il microfono me lo dimentico sempre. Ok, allora. Ok, so what we were doing yesterday was to study how to solve specific type of equation by using the Fourier decomposition. We will still spend some 5-10 minutes to discuss how to solve equations in which the boundary conditions are not just zero. Let me make a comment that is important, a general comment on what we are doing. So, why are we discussing this technique of Fourier? And is this technique, so to say, sufficient? And then why to study other techniques or not? First point, we are studying for the moment very simple equations. Which are typically one-dimensional equations, just space. But as I think I mentioned time ago, if we are able to solve the time-independent problem by using this Fourier decomposition, then we can also solve the time-dependent problem essentially just by giving a time dependence to the coefficients of expansion. So the technique from this viewpoint seems very powerful. And if you open some relatively old book on partial differential equations, it was mainly, those books were mainly discussing the Fourier decomposition. So why today, and most of the next lessons, we are instead going to study other techniques. The point is that this technique is fine if you can compute the eigenfunctions. And of course, you can do that if a problem is very simple. I mean, in the trivial cases that we have discussed, we were just getting sinus functions. And so when it is simple to evaluate the eigenfunctions, in most cases, the Fourier decomposition is absolutely fine, and it's easy, and you can use it. Point is, in many real-life cases, it is not easy to evaluate, to compute the eigenfunctions, in the sense that in many real-life cases, there is not even an analytic solution to the eigenvalue problem, meaning that you can solve numerically the eigenvalue problem, obtaining numerically the eigenfunctions and the eigenvalues, but as I said, not analytically. I mean, there are equations which are just slightly more complicated than the equation we are discussing, and for those equations, so simply there is no analytic solution. So still one can say, okay, but then what's the problem? We can numerically compute eigenfunctions and eigenvalues, and after we keep using the Fourier decomposition. The problem is that in many cases, to obtain numerically one of the eigenfunctions is a problem that for the time needed, the complexity of the technique and whatever, is completely similar to the problem of solving directly the partial differential equation. So there is no advantage in numerically computing the eigenfunctions if the purpose is to compute actually not just one, but a relatively large number of eigenfunctions and after to expand, etc., etc. So that would be really time consuming, not very efficient. And that is why today we are going to discuss another technique, which is the technique of the finite elements. So, okay, so this is, I mean, why we are discussing this Fourier decomposition and the limits of the Fourier decomposition. Okay, to conclude this discussion of the Fourier decomposition, let me mention one question that we have not yet addressed. And the question is, what happens if we have, let's say, for instance, Dirichlet boundary conditions, but so boundary conditions in which we give the value of a function at the two extreme, but we don't put to zero the value of a function. So let's be concrete. And let me write something. A second. Okay, so let's assume that we are discussing a problem like similar to the previous one, that is minus t, second derivative of u respect to x squared equal to f of x, and this, as usual, in a certain interval. But this time, we are saying that u of 0 is not 0, but is equal to a, and u of L is equal to b. Okay. So how do we solve this problem? You have seen how to solve a problem when a and b are equal to 0. So we know how to solve that problem, and we can easily transform this problem in which the boundary conditions are not homogeneous, they are inhomogeneous. We can transform this problem back into the previous problem. And the trick is very simple. Suppose that you introduce a sort of auxiliary function, a linear auxiliary function, p of x, which is of the form alpha x plus beta. So, first point, if I have a linear function like this, I know that the differential operator is just annihilating this function, meaning that if I apply second derivative to this function, I just get 0. So this means that if I have a solution of the original equation, and for a moment I forget about the boundary conditions, I can always add a function like this p of x, because it's not really modifying the left-hand side. So I can use this function p of x in which way? By imposing that p of x satisfies the two boundary conditions. So I impose that p of 0 is equal to a and p of L is equal to b. If I impose these two things, I come to the conclusion that p of x must be a plus b minus a over L x. You can easily check that, of course, this specific p of x satisfies both boundary conditions. So at that point, what can I do? I can shift, so to say, the problem. I can, here I had u, which is the solution of the original problem, and I can introduce a v function, v of x, which is equal to u of x minus p of x. So p of x is fixed, it has now been determined completely by imposing that it satisfies the two boundary conditions. And it is obvious that what happens if I write the equation for V. The equation for V, I mean the second derivative here, as I already mentioned, is exactly identical to the second derivative of U, because the second derivative of P is equal to 0. So this means that if I substitute inside there, I get that the equation for V is of a form minus T, second derivative of V respect to x squared, equal to f of x. So it's the same equation as the equation of U, but this time, which are the conditions I have to impose on V of x? Well, U of 0 has to be A, but we already know that P of 0 is A, so V of 0 is equal to 0, and similarly, V of L is equal to 0. So essentially, sorry, what we do when we have these not homogeneous boundary conditions is, first of all, we introduce this auxiliary function that satisfies the two not homogeneous boundary conditions. And after we solve this problem, which is a problem with homogeneous boundary conditions, using the same technique that we discussed last time. And when we have determined V of x, of course, U of x, the solution of the original problem, is just V of x plus P of x. Oops. And this solves the problem. Okay, so this is the way how to deal with not homogeneous boundary conditions. So let me just again once more summarize this Fourier technique. So this Fourier technique works if we have a differential equation that corresponds to a symmetric operator. The reason, as we mentioned already many times, is that for a symmetric operator, we have real eigenvalues, and for each eigenvalue there is one and only one eigenfunction, and eigenfunctions belonging to different eigenvalues are orthogonal. So we can form a basis, and we use that basis to expand everything, to expand f of x. You recall the discussion that f of x not necessarily has to satisfy the same boundary conditions of the problem, but still the technique can be used, and we expand the solution. What really matters is that we use as a basis the eigenfunctions obtained by imposing the same boundary conditions of the original problem, meaning that the solution that we are building through this expansion satisfies exactly the same boundary conditions as the eigenfunctions. This is what will guarantee that the Fourier series is converging rapidly and point-like, because we know that instead the f of x, the convergence of the Fourier series for f of x is not point-like. Okay, that's it for this Fourier. Maybe we can still discuss another time another little numerical problem, but they are all very similar. So okay, let's see if it is the case or not. And let's move to another technique that it is the main technique that we are going to discuss for solving this type of problems. This technique, as I said, is called finite element method of different technique or whatever. So this technique is based on a few ideas that I'm going now to discuss. Essentially, it's based on 3 steps. The first step that we are going to discuss today is that it is possible to define and to write the problem that we are discussing. We are discussing a problem which is a differential equation with boundary conditions, so boundary value problem. When you state this problem giving a differential equation with 2 boundary conditions, you say that you are formulating this problem in the strong form. Okay, the strong form is just what we have done up to now. But we are going to see that it is possible to express the same problem in a different way, a way that will correspond essentially to a sort of integral equation, okay? Or if you prefer, a sort of variational principle. And that new formulation that we are going to find is completely equivalent to the strong form, and is called the weak form. So we will have this weak form of a boundary value problem that is the same problem, but is not formulated by giving a differential equation with the boundary conditions, but rather through a sort of integral equation. So it doesn't look like we are gaining so much, because the point is we have just shifted the difficulty of the problem, in the sense that we had a differential equation, meaning that we have to determine our solution in each of the points. But if you think in terms of a matrix, it is the same as having a matrix with infinite components, continuous number of components. Of course, you can try to discretize, etc., etc. But and now we will have instead another problem, which is, as I said, a sort of integral equation, or better, a sort of variational problem. But again, in principle, in this problem, the number of degrees of freedom will be infinite. So it seems that you're not gaining too much. So now comes the second ingredient. The second ingredient is a little theorem by Galerkin. And this Galerkin technique is essentially solving a small but relevant technical problem. So as we will see, okay, we can formulate the boundary value problem in the weak form, okay. And to try to solve it, again, we can try to write everything by using a base, let's say, a base containing, in principle, an infinite number of elements. But of course, we cannot deal with that. We cannot deal with a base with an infinite number of elements. So if we want to use that expansion, we have to truncate the expansion. So the question is, if I truncate the expansion of a solution, let's say I take the first 10 terms in a certain expansion, am I sure that I am, so to say, getting the best approximation to the solution of the original problem, or maybe there was some better way of performing this truncation? I mean, does it make any sense, as we will see better probably next time, does it make any sense to just claim that we are restricting ourselves on a certain subspace which is not infinite dimensional, so the number of elements of the base is not infinite, it's finite, and so we just write essentially the same equation but rewritten into this finite dimensional space. Is this consistent? Is this sort of truncation consistent, or there is something wrong? And it's possible to demonstrate technically that the way in which we will make this truncation is technically correct, in the sense that we will get, through that rewriting of the equation, the best approximation to the solution that is possible to obtain truncating up to a certain element. So the second ingredient in this approach is a sort of check of consistency. The check of consistency is, okay, it seems clear that I could rewrite that complicated equation just limiting myself to a certain subspace. But is this correct? Or am I introducing some arbitrariness in the calculation? The answer is, yeah, the way in which we are restricting ourselves to the subspace is consistent. We will get the solution, we will get the better approximation to the original problem, to the exact solution, truncated in that subspace. There is consistency between rewriting the equation in a certain form and thinking that somebody very, very smart gave us the exact solution, and now we are just taking the best approximation of the exact solution if we limit ourselves to a certain subspace. So this is the Galerkin method or whatever. So first step is rewrite the strong boundary value problem in another form that will involve an integral and can be interpreted as a sort of variational approach. Second step is, okay, but still, I should span a space of infinite dimension. I don't know what to do. No, that restrict to a finite dimensional space, and this is done in a very consistent way. Third ingredient, because one can say, okay, but you are still speaking about a base. So which is the advantage? I mean, the problem that we were mentioning before was that it was difficult to determine the elements of the base, not the Fourier decomposition. In fact, we are not going to do a Fourier decomposition. We are instead choosing a certain number of functions that constitute a base, but this base is made of elements which are very simple functions. So altogether, we are going to show that essentially it will correspond. You want to have a way of approximating whatever function which is, so to say, defined between A and B, okay? So you have this very general function, and you want to approximate this very general function as a superposition of simple functions which are localized. Imagine that you have some sort of Gaussian, for instance, that is centered in a certain point with a certain width, okay? And it essentially is different from zero only in that area. We will use something even simpler than a Gaussian. We will use a sort of step function, okay? But the idea is that, okay, of course, if I introduce enough of these localized functions, I can approximate the original function to the degree of precision that I like, that I want, that I need. Okay, so I will not really resort to the Fourier decomposition. I will use a very simple base of localized functions and a finite number of them, and I will be sure that what I'm doing is not horrible, because Galerkin is telling me, no, if you rewrite the equation in that way, you are not introducing some arbitrary truncation. You are truncating, but in a way which is at least consistent. So these are the three steps. The three steps are rewrite the problem in a way that involves a sort of integral, accept the fact that we have to truncate still the space, but checking that the truncation is done in a consistent way, expanding everything on a finite element basis. That's why it's called finite element techniques. But these elements of the base will be very simple functions. This will have a lot of practical advantages that we are going to discuss in the following. Okay. So let's start. And to start with, so the first part of this problem can also be decomposed in sub-problems. So what we want to do to start with is we start with our differential equation, and we want to try to understand if this differential equation that recall corresponds to a symmetric operator can be reinterpreted as a problem in which I define a potential energy. So essentially, the first part of this reformulation is to say, I have a certain differential equation. Can I interpret the differential equation as an equation where I am determining something, a function, that will minimize a certain potential energy? So how can I define that potential energy? And can I show that the potential energy defined in that way has a minimum in correspondence of the solution of our differential equation? This is the first step. This first step is divided in two sub-steps. The first sub-step is to consider what happens if we just concentrate on the first part of the differential equation. So the homogeneous part without the f of x. Why we do that? When we discussed some of our partial differential equations, for instance, I don't know, the equation of the waves, you recall, or also the equation of diffusion, you recall that this f of x, this not homogeneous term, for instance, in the equation of the waves, was corresponding to some external force. So before introducing the effect of the external force, let's discuss how we rewrite the first part of the equation, this left-hand side, introducing some sort of potential. This will correspond to the potential of the internal forces, that, for instance, could be the tension, the elastic force inside the string or whatever. So the first part of this sort of Chinese boxes problem is to concentrate on the homogeneous part of the equation, so without this f of x, and rewrite the problem showing that we can introduce a potential, and after we will modify the potential, trying to incorporate the effect on the potential of this external force. Okay. Okay, let's start. So let's start from the following problem. So as I said, we are concentrating on the homogeneous equation, but I mean, this was time independent. Let's go back to the time dependent problem. Okay. So let's consider the following problem to be clear. Let's say the equation, for instance, of the waves that could be written as there was an A that is really irrelevant. There was the density, rho of x, second derivative of u respect to time squared. So let me tell again, we are considering the homogeneous part of the equation, but we are discussing also the time-dependent part, okay? Minus a, and as you probably recall, this is a very, very, very special and simple case of the part of the equation that contains the space derivatives. More in general, that can be written as derivative respect to x of k of x, which was the elastic constant that actually depends on the position, du over dx, and this is equal to 0. Okay, and we are going to solve a problem as usual between 0 and L, and let impose some boundary conditions in the form u of 0 at all times t. So Dirichlet boundary conditions and actually homogeneous boundary conditions, and u of L and t equal to 0. Okay. So what I have done is essentially just to consider the more general form of the equation that we discussed before, including the time dependence, and also considering the possibility that this k of x depends on x. So this is what we were obtaining when discussing the equation of waves. So, okay, this is our equation, and essentially we want to transform this equation in order to show that the solution of this equation corresponds to the minimum of a certain potential. Okay, so let's see how to do. We have to define essentially this potential energy. So to define this potential energy, we can multiply this equation by du over dt. So let me write it here. I multiply this equation, okay, doesn't matter, du over dt. Okay. So I can rewrite all this in the following way. I can rewrite, of course, a rho of x, and okay, doesn't matter. Okay, I mean, the u over the t I can bring inside, doesn't matter really. The next step, one of the problems of the book is that is very, very slow in its elaboration, too slow sometimes. Okay, so the next step is to integrate this new equation here from 0 to L. So let me do this little step. So I get integral from 0 to L of the A is really relevant. I can put anywhere. And I have these two terms. So I have rho of x, second derivative of u respect to time square. Can you read what I'm writing, or is it a bit too faint? It's too faint, isn't it? Just a second. I don't know why always changing. Let's see if now. So the first term is this object, du over dt. Okay, now it seems better. Okay. Minus, so this was the first object, minus the second object, which is derivative respect to x of k of x du over dx, and here we have du over dt, and this has to be equal to 0. Integrating dx, this has to be equal to 0. So what I've done is just to take the original equation and multiply by the u over dt and integrate from 0 to L. So now we are manipulating a little bit the various pieces so that we will be able to appreciate that these two terms will essentially originate one term that will correspond to the kinetic energy, and the second term will correspond to the potential energy. So just to do a little manipulation. So for instance, let's take the second term, the one containing the space derivatives. And we can rewrite by performing a partial integration. So let me do that. So instead of writing minus integral from 0 and L of this derivative respect to x of k of x du over dx du over dt integrated dx, I perform a partial integration, and so I get minus k of x du over dx. Okay, this was really not needed, this parenthesis. Okay, sorry for parenthesis. Du over dt evaluated at 0 and at L. And we get a plus the integral between 0 and L of k of x du over dx, and here we get the second derivative of u differentiated both respect to x and respect to t, integrated dx. Okay. So we are concentrating on this piece here. Okay, this piece can be partially integrated. The first term is 0. Why is 0? Recall that we have imposed these boundary conditions, and these boundary conditions are imposed for all times. So if I ask myself what changes, how u changes with time at 0 and at L, therefore du over dt evaluated at 0 and at L, the answer is 0. It's not changing. Okay, we write this explicitly. This implies that the u over dt evaluated at 0 is equal to 0, and the same is for L. Okay. So this object here now vanishes because of the time-independent boundary conditions. Okay, so this is the first point. The second point is I can rewrite still this object. Sorry, not plus but equal. Sorry. I can rewrite still this object here in the following way. I can rewrite as an integral between 0 and L, k of x. And if you think a moment, this can be written as 1/2 the derivative respect to time of du over dx squared integrated dx. I mean, if I take the derivative respect to time, the 1/2 and the 2 cancels, I get a du over dx, and after I take another derivative respect to time of du over dx, which is the second element. Okay, so we have been able to rewrite the second term of the equation, this piece here, as a time derivative respect to time of a certain quantity. K of x does not depend on time, so I can write this just as a derivative respect to time, okay, of 1/2 this integral between 0 and L, k of x du over dx square dx. Okay, so this is the second term. Let's now manipulate the first term. Okay, that is not too complicated. So the first term contains a second derivative respect to time multiplied by a du over dt. And I can rewrite in a similar way as a derivative respect to time of 1/2 du over dt squared. Because if I take the derivative, okay, the 1/2 and the 2 cancel, I get a du over dt, and then a second derivative of u respect to time. So also the first term, this term here, can be written as a derivative respect to time of an integral containing this part. So altogether, that equation can be written as a derivative respect to time of what? Of 1/2 the integral. Okay, the a is really relevant. I can put this a everywhere. It doesn't really matter. Of the integral of rho of x du over dt squared dx plus the other term, which is the first that we were discussing, which is again something of a form 1/2 integral, and this is integral from 0 to L, of course, integral from 0 to L of the a I put in front of k of x, and I have here a du over dx square integrated dx. And this we know that is equal to 0, because this is still our original equation. So recall what we did. We started from the original equation, we just multiplied it by the u over dt, we integrated, we performed just a few partial integrations. But this was, we were assuming that this equation was satisfied, that the u was satisfying this equation, okay? And because of that, now we arrive to the conclusion that that equation implies that the derivative respect to time of this quantity is equal to 0. So if u satisfies that equation, then there is this quantity in brackets that is time independent, remains constant with time. So it is clear that we can claim that this is a sort of total energy of the system. And this total energy of the system contains, as we see from here, two terms. There is a term where there is u, which is a displacement derivative derived respect to time. This is a velocity. So clearly the first term is some sort of kinetic energy. And the second term is instead some potential energy. So what we have done up to now is, first of all, to check that for the homogeneous equation, we could rephrase that equation as an equation in which there is a quantity which is conserved. This quantity, this total energy, is made of two pieces, a kinetic term and a potential term. So I am able to identify the potential energy associated with the internal forces, with the tension, for instance, with the elastic forces. Okay. So this is.
Prof?
Sì.
Sarebbe l'azione quella lì?
No, l'azione, no, the action, as you recall, is something slightly different. An action is the integral of the Lagrangian over time. While this quantity here that I have written, which remains constant, contains a first term. If you look to the first term, so there is the u over dt. U is the displacement, so the u over dt is a velocity, velocity square. Rho is a density, density of mass. So this is really something as a mass velocity square. So this is clearly a kinetic energy. The point is, so to say, I was not sure how to write the potential energy for this problem, and I have now obtained the form of a potential energy. What I know is that, I mean, this total quantity in brackets remains constant, it's time independent. And the first term is the kinetic energy. Therefore, the second term I can interpret as the potential energy. So this is the total energy. The action is defined as the integral of the Lagrangian. Okay, so it's a different animal. It's a double integral on space and time of the Lagrangian. Okay, so and as you recall, there you are. I mean, there is also, of course, a variational principle. You are looking for stationary. I mean, you are looking for extremes. You are extremizing the action, stationary point or stationary trajectory, or stationary values of the fields, depend if you are in one particle, many particles, field theory, whatever, of your action. But that is the Lagrangian approach. Okay, we are not really studying now the Lagrangian approach. We are, in a sense, studying something which is more similar to an Hamiltonian approach. We are introducing the total energy, the potential energy, and so forth. Is okay?
Yes, thank you.
Okay. So, okay, the next step is to try to understand. So this second term here, as I said, we can claim is the potential energy just due to the inner forces, to the elastic forces. But our equation in principle contains some external force, this f of x. So how to introduce a modification to the potential energy due to these external forces? So here we are studying one specific problem, which is essentially the problem of vibration of a string. So let's be very concrete, just to try to understand. So let's assume that this is our string. And okay, if there was no gravity force, then the equilibrium position would be this one. I mean, just the one in which we just get u equal to 0 everywhere and forever, and you are happy. U, let me remind you, is the deformation. So this, oops, this is u, okay? This is u, okay? This is x. So this is u of x. Okay. So we have our string, and now assume that there is an external force, let's say the force of gravity. So the force of gravity is clearly pulling down the string. So we have chosen the axis in this way. So choosing the axis in this way, it means essentially that, okay, the force of gravity is pulling in this positive direction, the same direction for which there is this deformation of the string. Okay, so what happens is that the string is pulled down. So if now I consider the effect of the external forces of the force of gravity on the potential energy of the string, okay, you recall that the potential energy is defined only up to a constant. Okay, the constant in general does not play a role unless you are in general relativity. Okay, so fine. I mean, the constant I don't really care. But what happens if the string is moved downward? I mean, in this direction. It clearly means that the potential energy of the object due to gravity is lowered. I mean, we are moving downward in the direction of gravity, our object, and its potential energy due to gravity, the contribution of the potential energy due to gravity is therefore reduced. So how to write this potential energy that is going to be reduced if the u of x is in the same direction of gravity? Well, let me just remind that the F that we have in the equation is not a force, it's better a density of force. So it means essentially that if I want to have, let's say, a force, I have to take F, I have to multiply by the famous A, and by some element, the X. So this A, the X, is a little element of volume. And so I am multiplying a density of force by an element of volume, and this corresponds to an element of the force. Okay. So if I want to now to evaluate the work done by gravity, I have to multiply the force by the displacement. And the displacement is u of x. So let's say that the work is indicated with an L. Be careful, but this L is not the Lagrangian. Okay, so L is the work, no? I think the work is lavoro, no? Okay, whatever. The L is this quantity multiplied by u of x. This is the work done by the gravity force if the movement of a string is in the same direction of gravity. So how do we modify our potential energy? As we mentioned, this work is reducing the total potential energy, because this was the contribution to the potential energy due to the internal forces, and this work will reduce the total potential energy that includes the potential energy due to gravity. So in conclusion, I can write a total potential energy, let me say A potential, and this A potential is made of two pieces. Is made of 1/2 integral from 0 to L k of x du over dx square dx, which is the term that we discussed before, minus I put an A somewhere, like here, okay, minus the integral from 0 and L of f of x u of x dx. And of course, I can say that, okay, there is some arbitrary additive constant, I call it epsilon 0, which is the potential energy due to gravity at the initial position, and this is reduced because of the action of the force. Okay. Is it clear enough up to now what I've done? Is okay? Yeah? No?
Yes, it is.
Okay, okay, thanks. Okay, so now we have just defined this sort of total potential energy, the one due to the internal forces, the one due to the external force, that in this case can be gravity. Okay, so what we are going to demonstrate now is that if u satisfies the differential equation, the original differential equation, then this potential energy, that of course depends on u, actually, if you write this in field theory, generally you write that this, generally write something like a potential is a potential depending on u, and also actually on the u over the x, obviously. Okay, this is the typical notation that you have when you write this type of quantities in field theory. So what we are going to demonstrate is that if U satisfies the differential equation, then this potential energy is at its minimum. We are at a minimum of the potential energy. Okay. So let's see how to demonstrate this. So let's assume that U satisfies the differential equation, and let's introduce something like omega, which is U plus some displacement V. Okay. So U, as I said, corresponds to the solution of the differential equation. And now I want to show that for whatever V, V still has to satisfy the boundary conditions. I mean, I am restricting myself to U, V, omega, whatever, that are all satisfying the boundary conditions. Okay. So what I'm claiming is that the potential energy evaluated at this omega is always larger or equal in the trivial case in which V is 0 of the potential energy of the potential energy evaluated at U. This is true for all V. Okay, this is what we are going to demonstrate now. So essentially this, we will reformulate this better, is the statement that the strong boundary value problem, meaning if I got the solution of the original problem with a differential equation, so the strong boundary value problem can be rewritten as a weak form of a boundary value problem in which I have a problem of minimization of the total potential energy. The strong, if I solve the original differential equation, I can show that this corresponds to the minimum of the potential energy. And to find the minimum of the potential energy essentially is what is called the weak boundary value problem, weak form of the boundary value problem. And of course, after we can just, for completeness, also show that the weak form is also equivalent to the strong. I mean, the strong implies the weak, but we also show that the weak implies the strong, so they are just completely equivalent. Okay, so let's demonstrate this little thing. So we want to demonstrate that if U satisfies the differential equation, therefore solves the strong boundary value problem, then this total potential energy that we have introduced is at its minimum. Okay. So to do that, we have just to evaluate this potential energy in omega, which is U plus V. Okay. So the potential energy is written here. So it's not very complicated. We can notice that after all, the first term is quadratic. Okay. So from the first term, we are going to get 3 terms. The one with U, the one with V, and the mixed term. And from the second term, which is linear, so we are going to get 2 terms. So altogether, we are going to get 5 terms. And actually, I don't know if I really need to do all the intermediate steps that sometimes it's really confusing. If you think a moment, it is clear that of these 5 terms, two of the five terms still contain U. Okay, because if I substitute here, I get something that will contain again the U over the x squared, and here I will get a term which is just U. So 2 of those terms are nothing else but epsilon potential of U. After I have other 3 terms, okay, let's write the other 3 terms. So from this object here, I get a term which is a mixed term. It corresponds the u over the x, u instead is u plus v, so it means, and it's square, so it means that I get the u over the x times the v over the x, double product canceling the two. So it means that from this term, I get in particular something as, okay, a is always there, and what survives is an integral between 0 and L of k of x, and I have a du over dx and a dv over dx dx. So this is the mixed term that I get from here, no? When I substitute instead of u, I put u plus v. This object contains v linearly, okay? Let me write for a moment the other term that I get from the second part, from here. So that other object is minus, you write it here, oops, minus a integral from 0 and L of f of x, v of x dx. So I have written the two terms which were containing only u. I already wrote them as potential energy of u. The two terms containing u linearly, containing v linearly, one coming from the mixed term of this object and the other coming from here. It remains the terms containing v quadratically coming from the first object. So plus 1/2, and the first object is a integral from 0 and L of k of x dv over dx squared. Okay. Is it okay up to now? I mean, the fact that these 5 terms can be regrouped in this way. Okay. So, they call what we want to demonstrate. We want to demonstrate the potential energy evaluated at u plus v is always larger than the potential energy evaluated at u. Becomes equal only if v is identically 0. Okay. So let's see if we are happy with what we obtained. What is written here, these two terms here, together, we can notice that actually together they give 0 if u satisfies the initial differential equation. This is what we are going to show now. So what I'm claiming is that the sum of these two terms is 0 for whatever v, if u satisfies the original differential equation. This is what we're going to check now. If we can demonstrate that, then we are happy, because we have a potential energy of u plus v is potential of energy of u plus 1/2 something that is clearly positive, because k of x is by definition positive, and v squared, and actually the point is, recall that u, v, omega, they all satisfy the boundary conditions. So the boundary conditions were, for instance, v of a equals 0, v of b equals 0, and therefore this object here, when it is 0, it implies that it is flat equal to 0. It's v of 0 everywhere. I mean, the derivative of this object equal to 0 implies that v is also equal to 0 because. So at that point, I would have demonstrated that the total potential energy at u plus v is always larger than potential energy evaluated at u is equal only if v is identically 0. So what remains to be demonstrated is what I indicated inside this red curve. This is 0 for whatever v. And let me try to do this now. So let me concentrate on that piece. And so let me rewrite, okay, let me drop the A. The A is really completely irrelevant. Okay, just, so let me rewrite this term, integral from 0 and L of k of x du over dx, dv over dx, integrated dx, minus the integral from 0 and L f of x v of x dx. Okay. So as usual, I manipulate the first term by performing a partial integration. What essentially I want to do is to have, here I have already a v of x, I want to have a v of x also here. So I integrate with the v over dx, and therefore I'm getting k of x du over dx v evaluated at 0 and at L, minus, and I get the integral from 0 and L, and I have to differentiate the other part. So derivative over dx of k of x du over dx v of x dx. So I have integrated by part this first object, so that here now I have a v of x, and still I have a second object. So the second object is minus the integral between 0 and L of f of x v of x dx. So let me remind, these are the two terms that I need to demonstrate that they add to 0 if u satisfies the original equation. Okay. So what happens that this first term here is 0 because v is arbitrary, but it has to satisfy the boundary conditions. So v of 0 is equal to v of L is equal to 0. So this object here is 0. And therefore, we are happy because, of course, we can just put together the two pieces and we get minus integral between 0 and L, and we get the derivative respect to x of k of x du over dx, and the other piece is plus f of x, all this multiplied by v of x dx. And of course we know that what is inside this bracket was the original equation, and therefore if the u is satisfying the original equation, then we are happy because this quantity is 0, and therefore this integral is identically 0 for whatever v. For whatever v. Okay. So we have demonstrated that if we have solved our strong boundary value problem, and we have obtained, okay, sorry, there is one thing that maybe I forgot to mention. Notice that the time dependence now in this discussion has disappeared, in the sense that we are considering time independent problems. So we have derived the potential energy. Okay, the potential energy is what is written here. And now what I am discussing are time independent problems. So for time independent problems, what I have demonstrated is that the solution of the differential equation gives a u which minimizes this potential energy. I mean, of course, if I have a time dependent problem, things are different in the sense that the system contains some kinetic energy, And as we know, there is a balance between potential energy and kinetic energy, and what is conserved is the total energy. But what I have demonstrated here is just that, okay, if I have a time-independent problem, I can concentrate, of course, the total energy reduces to the potential energy, and what I have demonstrated is that the solution of the time-independent problem, strong version, the differential equation, gives an object that minimizes the potential energy. Okay? So this is strong implies weak. Okay? The next step will be to demonstrate that weak implies strong. Before doing that, let me make a little comment. Let me rewrite a moment again what we have written. So we have written that the potential energy, that depends on, you recall that I wrote it depends on u and on the u over the x. This is the way in which you should write if you are, so to say, typically what you write in field theory, because we know that our potential energy contains a term, the second term that is explicitly evaluating u, but the internal forces instead depends on the u over the x. Okay. So in principle, u and the u over the x are in a sense independent. Okay. Anyway, this is just a little detail of notation. So if I forget about this little detail, what I have demonstrated a moment ago is that epsilon potential of u plus v is larger than the potential energy at u. Okay. And in particular, we have demonstrated that this is equal to a potential energy evaluated at u plus something linear in v plus something quadratic in v. Now, point is, this energy is a functional, meaning that it takes a function, u, and it provides a number. Okay. So in principle, I can evaluate a derivative of epsilon respect to u. That is what is called a variational derivative. You have seen this when you were studying classical mechanics, for instance, and therefore the minimization of the energy, or to find the stationary point of your action, for instance, you were systematically introducing those variational derivatives. So what I want to stress is just that I can, in principle, evaluate something which is this variational derivative of a potential energy respect to u of x. You recall this type of notation means essentially the following, means that I have to take the derivative. It means essentially the following. No, sorry. Did I formulate it better? Sorry. Let me write the variation. Let me write the variation delta of the potential energy of u. And this variation of the potential energy I can write as the derivative of the potential energy respect to u of x times a variation delta u x, of course, plus the derivative of the potential energy. Recall the potential energy depends on u and on the u over the x. So that is why it makes sense to write derivative of potential energy respect to the u over the x, variation of the u over the x. Okay. Yeah. Okay. So this is what is called after if I divide this by delta u, which is what is called a variational derivative. You recall that this object here can be rewritten. I mean, I can rewrite that the variation of the u over the x can be written as a derivative respect to x of a variation of u. Okay. So in conclusion, what I can do is to take a sort of variational derivative of a potential energy respect to u. And this variational derivative contains a first term, which is just the derivative of the potential energy respect to u. And the second term that, okay, the notation is not extremely smart, but I don't think is completely wrong. The second term is the derivative of the potential energy respect to the u, which is a u, u, not a mu. The u, sorry, let me write it better instead. The u over the x. And here, let me just write derivative over the x. This looks, of course, a little bit funny because, I mean, what does it mean, this object here? It means that will be applied on the function that I'm going to introduce when I'm actually acting with this object on another function. So what I am producing is a sort of functional, and this functional will act on a function, and this is the operator that will act on the function. So this is a sort of variational derivative, and therefore what I can do is, for instance, to project this variational derivative on a certain direction. Let me introduce the scalar product of this derivative of the potential energy, variational derivative of potential energy, scalar product with a v of x. So what happens if I do that? This scalar product, you recall, is defined as an integral, and therefore this integral is the integral between 0 and L dx of these two terms, okay, derivative of epsilon respect to u plus derivative of epsilon respect to the u over the x multiplied by v and integrated on all the x. Now what happens if you write explicitly what is the derivative of epsilon respect to u? This is just f, okay, and the derivative of epsilon, because epsilon was written here. So very sorry, there is a minus sign. I was already forgetting the minus sign. So there is a minus sign. Is minus. Oops. This is minus f. While this object here is the object which contains the k, the u over the x. So what I am writing here is that this, which is a sort of projection of the variational derivative in the direction of v, This object can be written as the integral between 0 and L dx of, let's write first the second term, of k du over dx dv over dx minus f of x v of x. Okay, so if you recall, this quantity here is exactly the two terms that we were getting in our expansion here. These are the two terms. So what I have shown slightly sloppy notation because I introduced, I just wanted to do this as fast as possible. These two terms that actually we know that they add to 0, we have demonstrated that they add to 0 if U satisfies the differential equation. They can be interpreted as the projection of the variational derivative of the potential energy in a certain arbitrary direction V. Okay, but what does it mean in conclusion of all this? You recall that if you take the derivative of a potential energy, let's suppose that you are in one particle dynamics. You have a potential energy and you take minus the derivative of potential energy respect to x, and what you're getting is a force. Okay, and after, if you multiply your force by a displacement, you get a work. Here, of course, we are not in mechanics of one particle. We have some sort of field. So this derivative that we have introduced is some sort of generalized force. And essentially what we are computing is the action of this sort of generalized force acting on a generic displacement that we call V. The force acting on a certain generic displacement. What we have just shown is that quantity is identically 0 if the strong boundary value problem is satisfied, because this is exactly what was equal to 0, no? We have demonstrated above. So what this means? This is what is sometimes called the principle of virtual works. I don't know if you have seen it in some course of mechanics, maybe. So this principle of virtual works tells us essentially the following, that if I am closer to a minimum, whatever displacement from that minimum corresponds to 0 work. Consider the simple case of one particle mechanics. You are sitting at the minimum for potential energy. The force evaluated there is equal to 0, because of course the du over the x is equal to 0 because you are at a minimum. Therefore, if you take that force, which is 0, you can multiply that force for whatever displacement, you still get 0. So this virtual work, it is just the work that you would virtually do if you were trying to do a little displacement respect to the equilibrium position, is 0. Here we have generalized to a system in which we have, so to say, infinite number of degrees of freedom, because I mean, we have degrees of freedom for each x. As you recall, you go from the mechanics of one point to this that essentially is field theory, because in the way that there x was meaning a position, therefore a trajectory, and here x is a sort of parameter, okay, indicating where position, and after t is another parameter at which we are evaluating the real movement, which is instead u. Okay, you recall this connection. Voila. Okay, so in conclusion of this, what we have demonstrated is that the strong boundary value problems also contains in its belly the principle of virtual works, meaning that if I have solved a strong boundary value problem, I have demonstrated that I am at a minimum of the potential energy, and I also can formulate that by telling that I am in a configuration U for which whatever virtual work I am doing, a little displacement respect to that position, corresponds to zero work. This is what is called, as I said, the principle of virtual works. Okay, does it make sense to you? Is all this? Okay. The last 10 minutes, I think is sufficient 10 minutes. We can demonstrate this the other way around. So instead, we have demonstrated that strong implies weak, and now we demonstrate that weak implies strong, and after we are happy for the lasagna. I don't have a lasagna, always a salad for lunch, it's so depressing. Anyway, whatever. Whatever. Okay. So weak implies strong. So let's start from the weak. So the weak is essentially exactly what is in front of our nose. I mean, this quantity here, we know that is equal to 0. And we know that this, the fact that this is equal to 0 corresponds to the statement that the potential energy is at a minimum. And this is, to say, the weak form of the boundary value problem. So recall one important point, that this is equal to 0 for whatever V. For whatever V. Okay, this is important. It's not that it is 0 because I have chosen V in a smart way. This is 0 for whatever V, because it is U which is special. U is the solution of that equation. After this is 0 always. Okay. So now let's reformulate and tell, suppose that I am in this situation. Suppose that I am in the situation in which this quantity here is equal to 0 for all V belonging to the space that I am discussing. What I can demonstrate is that then the strong boundary value problem is satisfied. The U is really satisfying that differential equation. And we do, as usual, the opposite movement. So we perform, again, a partial integration. So the first term becomes K of X, the U over the X, V of X, evaluated between 0 and L, minus, and this is the integral between 0 and L, the X of K of X, the U over the X, and this has become V of X. So I have partially integrated the first term minus integral between 0 and L, the X of F times V. Okay, so we know that this is 0 for whatever V satisfying the boundary conditions. So this is 0 for all V satisfying those boundary conditions. So this means that what is in the first term is again 0, because V of 0 is equal to 0, V of L is equal to 0. So we are back to this. So now we know, essentially, that the integral between 0 and L, the X of K of X, sorry, derivative. Oh, sorry, I forgot to write derivative to X. Sorry. There was something missing. Sorry. I forgot to write derivative respect to X. Now, why I cannot insert? I wanted to insert something, but okay. I mean, here there is, sorry, here there is a derivative respect to X. So I forgot it. Okay. So what I'm doing here, okay, eraser. what I'm doing. Yeah, okay. So okay, finally. So this is equal to 0. This means essentially derivative respect to x of k of x, the u over the x, okay, plus the minus sign I put in front, okay, plus f of x, all this multiplied by v of x equal to 0. And this, again, is true for whatever v. If this is true for whatever v, I claim that what is in bracket, it must also be 0 for all x, meaning that u satisfies that differential equation. Why is that? Suppose that what is in bracket is not identically 0. Suppose that it is different from 0, for instance, in a certain region, values of x. Then I can choose a function v of x, which is localized, is different from 0 just there, okay, and is essentially just sampling that range of values of x, and if what is in bracket is not 0, it provides something that is not 0. So it means, in conclusion, that what is in bracket must be 0 for whatever x, and therefore we have demonstrated that the weak form of a boundary, of a boundary value problem implies the strong form. Implies the strong form. Okay, I think that we are done. And questions, remarks, objections, whatever. Is it clear enough?
No questions. Yes, it is clear. Thank you.
Okay. This book is very, very worldly. I mean, it's very slow. I discovered recently that the same author, Mr. Glockenbach, wrote another book. Let me just tell that I have not really bought the book. Don't ask more than that, okay? And so I found this other book that discusses only finite elements method. And probably you can find that book as I did, okay? And there is an introductory chapter that, I mean, for our taste, I mean, taste of people doing a master degree in physics, is probably slightly better because there are a little less small steps and a little more concrete things. But I discovered it 1 or 2 nights ago by chance. So maybe next year I will rephrase a little bit things using that book because I think it's slightly better. So this book is okay, but it's written, I suspect, for engineers, so it goes very slowly through all the little steps, and sometimes instead it's somehow missing a little bit the general frame, because if you, as you know, if you concentrate too much on the tree, you stop seeing the forest. Who told that? Was it Shakespeare? Must be Shakespeare. Okay, so with this Shakespearean quotation, I wish you a nice end of the week and see you next week.
Thank you very much. Prof?
Sì.
Posso chiederle una cosa finale?
Certo.
Se può lasciarci il titolo
Sì.
del corso?
Lasciavi le cose che ho fatto l'anno scorso, è vero? Quei 2 esercizietti, è quello che dicevi.
Ah, anche quello. Sì, no, ma anche il titolo del libro.
L'altro libro che ho trovato, del stesso autore, e si chiama Finite Element Method.
Ah, ok, perfetto.
Lo trovate banalmente in quel modo lì, in sostanza. È un libro molto più tecnico, specifico. Di per sé sarebbe anche interessante, però diciamo che la cosa che mi sembra buona è che il primo capitolo, che fa un riassunto in pratica di quello che discute per certi versi più a lungo in questo libro, però quel riassunto è conciso e abbastanza utile.
Ok.
Quindi forse in futuro farò questo switch da quella parte lì, perlomeno questa parte qua la prendo anziché da questa versione del libro di sto qua, insomma, dall'altro perché mi sembra più adatta a noi, diciamo, cioè qua lui perde tempo a fare dei passaggi insomma, abbastanza irrilevanti, invece di là va più sulla ciccia, che mi sembra utile, insomma.
Ok, grazie mille. E poi sì,
sì, devo metterli, sì, devo correggere quelle 2 note che ho messo che non erano esatte. Oggi pomeriggio le correggo e ve le metto sul Google Class, come si chiama.
Ok, grazie mille.
Bene, buon fine settimana. Ciao, ciao.
Grazie, prof.
Ciao, ciao, ciao.
Arrivederci.
Ciao, ciao, ciao. Allora, dunque, qua. Allora, come si fa qua? Stop record.